Hi, I'm Bill Kuszmaul. I'm a fourth-year PhD student at MIT, and this is joint work with Michael Bender at Stony Brook University and Bradley Kuszmaul at Google Cloud. The title of this talk is Linear Probing Revisited: Tombstones Mark the Demise of Primary Clustering. And I want to spend the start of this talk just talking about a classic data structure that we all learned in undergrad, the linear probing hash table, and summarizing some of the classical results about it. Then in the second half of the talk, we'll come back and we'll see that actually there's some kind of surprising new results that suggest that our classical way of thinking about linear probing maybe isn't quite right. Okay, so a linear probing hash table is a data structure that stores elements in an array, and it supports three operations: insertions, queries, and deletions. To insert a new element, all you do is you compute a hash of that element, mapping you to some random position in your hash table, and then you scan forward until you find a free slot where you can place that element. That's insertions. Queries are essentially the same deal. So if you want to figure out whether an element X is in your hash table, you again hash that element, and then you scan forward until either you find the element you're looking for, meaning it is in the hash table, or until you find a free slot, which means the element you're looking for actually isn't in the hash table. That's queries. Deletions are actually a bit more complicated. So it turns out there's several different ways you can go about implementing deletions. But the most classical, and the one we're going to be using today, and we'll see that this is actually an important distinction, is that when you want to delete an element, you just mark it as deleted. You replace it with what's called a tombstone. And what's interesting about tombstones is that they actually behave asymmetrically in how they interact with future insertions and queries. So when a future insertion comes across a tombstone, it actually overwrites that tombstone with the element currently being inserted, essentially treating the tombstone like a free slot. On the other hand, queries do not get to treat tombstones like free slots. When a query comes across a tombstone, it actually has to keep looking for the element that it's searching for because that element might be to the right of the tombstone. And one consequence of this is that if you have too many tombstones in your hash table, you can actually hurt your query performance. So the final detail in implementing a linear probing hash table is that every so often you should rebuild your hash table from scratch and clear out all the tombstones. So that's something we'll be assuming throughout the talk, is that your hash table is rebuilds every so often and that you've selected the rebuild frequency to be the optimal one. But if you do this, then tombstones interact nicely with both insertions and queries, and you'll end up with a hash table where all of your operations, insertions, deletions, and queries, behave properly together. So that's classical linear probing. And one thing that's interesting about linear probing is it was introduced in 1954. It's been around now for nearly 6 decades. And despite that, it actually still remains one of the most widely used data structures today. So why is that? Well, there's a bunch of good things about linear probing. It's relatively simple. It's relatively space efficient. For example, it doesn't have any pointer overhead. But the thing that really makes linear probing phenomenal, and the thing that still gives it a competitive advantage today, is that linear probing has just incredible data locality. That means that each operation accesses only one small contiguous region of memory. So what that meant in 1954 is that on the IBM 701 machine, each operation might access only a single drum track. And since drum tracks took a lot of time to access, that was a big win. But what it means today is that on a modern machine, each operation now might access only a single cache line. And again, since cache lines are slow to access, it's still a big win. So this means that from an engineering perspective, linear probing is one of the best hash tables that you can use. That's the good news, but on the other hand, linear probing also famously comes with a corresponding set of bad news. And to see that, all you have to do is analyze the average time of a given insertion. So let's suppose that we've just filled our hash table up to be a 1 minus 1 over x fraction full. For example, if x is 100, then the hash table is 99% full. And actually, x is the one variable that I'm going to want you to remember through the rest of the talk. Okay, so how much time would it take for us to perform one more insertion? Well, the intuition that undergrads typically have when they learn about linear probing is that if 1 in every x positions is free, then the amount of time that it should take for us to find a free slot should be roughly order x. And in fact, this intuition was so strong that in the late 1950s, when linear probing was first being studied, researchers went so far as to say that it seemed almost certainly that this must be what's going on. And it seems hard to prove, and in fact, when you graph it, it seems to behave a little strangely, but surely this must be what's happening. And then in 1963, Donald Knuth came along, and this was actually a historically important paper because this was actually Knuth's first paper in the field of algorithms and data structures. And what he proved is that actually the expected insertion time isn't order x, like you might first expect. It's actually quadratically larger. It's order x squared. And the phenomenon that Knuth had observed is what is today known as primary clustering. All primary clustering says is that as you put elements into a linear probing hash table, they have this tendency to cluster together into runs that are longer than you might first expect. And the way that textbooks typically explain this is as a winner keeps winning phenomenon. The longer that a run of elements gets, the more likely it is to accrue additional elements, which creates kind of a positive feedback loop. It turns out that's not really the full story. So in particular, if that was all that was going on, it turns out that primary clustering would only have a constant factor effect. And Knuth actually talks about this in his early work. He explains that really the main thing that's going on here is actually this globbing together effect. When you insert an element, it might not just increase the length of a run by 1, but it might actually connect together 2 already long runs. And that, especially when you combine it with this winner keeps winning effect, that's what causes primary clustering. That's why there's this quadratic blowup in the expected length of the run containing any given element. Okay, the last thing that you need to know about linear probing before you're kind of caught up to the state of the art is that primary clustering is actually an asymmetric phenomenon. So it affects insertions, but not queries. And the reason is because it turns out there's a neat trick you can use to make your queries fast despite primary clustering. And this trick was introduced by Amble and Knuth in 1974. The idea is that within each run of your hash table, you actually store the elements in sorted order by their hash. So for example, if you have a run with elements whose hashes are 5, 5, 6, and 6, you store them in this order. So this does require you to slightly modify how you do the operations in your hash table. For example, if you're doing an insertion, then what you do is you find the position where you want to insert your element into, and then you slide all the elements after that to the right by 1 until you get to a tombstone or a free slot. So if you're careful about this, you can maintain this invariant that your elements are sorted by hash. And what's cool is this means that queries don't actually have to go to the end of the run. For example, if you're querying an element with hash 5, you can stop as soon as you encounter any elements with hashes 6 or larger. And so even though the expected length of the run that you're querying in is x squared, it turns out your queries still take time order x. In other words, primary clustering really is a phenomenon about insertions. Okay, so putting the pieces together, this is the situation we've been in for about 5 decades now, is that linear probing is this really nice natural hash table design. And the queries are actually pretty fast. They take time order x if your hash table is 1 minus 1 over x fraction full. But the insertions are problematically slow. They take time order x squared on average. And so the classic takeaway, the thing that's taught in courses, taught in textbooks, is that linear probing shouldn't be used in a hash table that's at a high load factor, in a hash table that's full. And so what hash tables tend to do in practice, for example, what the open source hash tables released by both Google and Facebook do, is they use linear probing when you're at low load factors, but then when you're at higher load factors, you intentionally make design compromises in the hash table design so that you can try to avoid this clustering, but at the cost of data locality. So you lose the thing that makes linear probing so great, which is its phenomenal data locality. And kind of the conventional view is that that's just the situation we're in. If you want space efficiency, then you can't have data locality. Okay, so this brings me to part 2 of the talk. And what I want to show you now is that actually there's more going on here than what the classical analysis might seem to suggest. In fact, we can actually get rid of clustering. And there's even an interesting sense in which it's already gone and we just didn't notice it. So what I'm not saying is that the classical analysis is wrong. It isn't. But the classical analysis does have a slightly narrower scope than you might first imagine. So in particular, the classical analysis is considering an insertion-only workload. You start with an empty hash table, you do insertions until it's 1 minus 1 over x fraction full, and you look at the expected time of the next insertion. But in some sense, that workload isn't really that concerning because, yeah, your final insertion has a large expected time, but the vast majority of your insertions were performed at much lower load factors. And so the actual average time per insertion, it turns out, was only order x. The more concerning case is what if you also have deletions? So in particular, what if you fill your hash table up to 1 minus 1 over x fraction full, but then you stay there, you alternate insertion, deletion, insertion, deletion, insertion, deletion. Then the conventional wisdom is that now all of your insertions suffer from primary clustering. And now each of these insertions takes quadratic expected time. But the thing that I want to emphasize is that this isn't actually directly implied by the classical analysis. Because the tombstones that get placed into the hash table when you do deletions, they have the potential to change the combinatorial structure of your hash table. And so in principle, the classical analysis doesn't, at least technically, apply. Now it turns out there are versions of linear probing, so there are alternative ways to implement deletions where the classical analysis does apply, so you really do get quadratic time per insertion. But if you're using tombstones, which is kind of the classical way of doing deletions, then the classical analysis doesn't apply. And this might seem kind of pedantic, but it turns out there's actually an interesting phenomenon here, which is that the tombstones that get placed by deletions actually cause an anti-clustering effect. So what's happening is that when you place a tombstone, you essentially break a run into two parts from the perspective of future insertions. And in fact, these tombstones that get created by deletions, I claim they actually asymptotically affect the expected time of future insertions. And this brings me to the first result from our paper. What we prove is that we say, okay, consider any sequence of operations on a linear probing hash table, insertions, deletions, queries. And suppose that you never fill the hash table past a 1 minus 1 over x fraction full. But you are allowed, if you want to, for example, just hover at 1 minus 1 over x fraction full all the time. Then it turns out the expected amortized cost per operation isn't actually order x squared. It's actually soft O of x. So in an amortized sense, when you're operating at a high load factor, the effect of tombstones is actually to almost entirely eliminate the effects of primary clustering. So when we first proved this result, we were kind of disappointed by this tilde above this O, because of course what this means is we're ignoring polylog x factors. And we thought surely the answer must be just big O of x. But surprisingly, it actually isn't. So what we were eventually able to prove is we said, okay, consider a sequence of alternating insertions and deletions in a hash table that's a 1 minus 1 over x fraction full. So we alternate between inserting a new element, deleting a random old element. And it turns out the average time per insertion actually isn't order x. It's actually at least slightly larger than x. So if you do out the lower order terms, we get a lower bound of omega x square root log x. So what this means is that actually tombstones almost entirely eliminate the effects of primary clustering, but there actually is still a little bit of clustering effect where you're getting slightly superlinear average insertion time. One thing that's interesting is what happens if you actually plot these results in practice. So if you just plot the average insertion time in a linear probing hash table, where what you do is first you fill your hash table up to 98% full, but then you start alternating insertions and deletions. And what's interesting is that our theoretical result actually shows itself kind of amazingly clearly in this graph. Because what happens is first your insertion time skyrockets because of primary clustering. But then as soon as you start alternating insertions and deletions, your insertion time almost immediately comes way back down. And this is kind of interesting because on one hand, yes, tombstones have an anti-clustering effect, But on the other hand, insertions and deletions are one for one here. So for every deletion that's causing anti-clustering, there's an insertion that's causing more clustering. And what's remarkable is the anti-clustering effect of Tombstones completely wins. So instead of just staying up here and hovering, our line comes way back down to nearly ideal performance for a linear probing hash table. And this is a phenomenon that, as far as we can tell, hasn't been observed before. It's kind of somehow flown under the radar, even though it's actually happening in real-world linear probing hash tables. Okay, I want to wrap up the talk by just kind of summarizing two other results from our paper. The first question we ask is, okay, can we take this observation that tombstones are so useful and use that observation to do even better? So we introduce a new form of linear probing. It's still a linear probing hash table, but with an interesting tweak that we call graveyard hashing. And graveyard hashing actually achieves ideal expected insertion time of order x for every operation. And not only that, but x is actually based on the current load factor when at any given moment. So this really is kind of completely eliminating the effects of primary clustering, at least asymptotically. And the trick, it turns out, is to make use of our observation that tombstones are so helpful. In particular, the idea is that, well, maybe tombstones are so helpful that even when we're not doing deletions, we should sometimes just artificially add extra tombstones into our hash table in order so that we can benefit from their anti-clustering effect. So we actually prophylactically place tombstones into our hash table to boost insertion performance, even on insertion-only workloads. And this might sound kind of abstract, but it's actually there's a very concrete and simple way that you can do this, which is that every order n over x operations, you rebuild your hash table. So in classical linear probing, the point of this rebuild is to eliminate the tombstones that are in your hash table, clear out the tombstones. Here, the point of our rebuild is actually, yes, to eliminate the tombstones that are currently there, but then to actually insert new tombstones spread evenly across the hash table. And the rule of thumb that we want to follow is that about a constant fraction of our free slots should become tombstones. And it's these tombstones that are going to make insertions fast until we do our next rebuild. It's these tombstones that are going to eliminate or kind of keep clustering down. So what's interesting is this really is just linear probing, except we've made just a slight tweak to how we do rebuilds. But besides that, insertions, queries, deletions, they all work exactly the same. And now the average insertion cost is order x. One thing I want to note here is that in some ways this result is kind of orthogonal to the other results we were talking about. The other results are saying that classical linear probing, the thing we already use, actually behaves very differently than how we've classically thought. Whereas this is saying, if we want to push that further, we can actually introduce a new data structure, a new version of linear probing that does even better. Okay, now the last result that I want to mention before I wrap up the talk is that one consequence of making insertions faster is that, of course, we also make our data locality even better. And so you can capture this formally by analyzing graveyard hashing in external memory. And what you get is that in the external memory model, if your data block size is capital B, and B is just anything asymptotically larger than x, then the average number of IOs, or cache misses, that you incur per operation is actually optimal. It's 1 plus little o of 1. And this is an interesting result because if you think about it, what would happen if B was, for example, smaller than x? Then in any given random data block in your hash table, you would expect to have less than one free slot. So you couldn't possibly hope for your insertions to take 1 plus little of 1 IOs. But we're saying as soon as B is even slightly larger than x, suddenly graveyard hashing gives you optimal external memory hashing. And this is interesting in that it improves over the state of the art previously, where B needed to be at least order x squared. That was due to Jensen and Pei in 2007. And the reason we're able to get this improvement is precisely because we've eliminated clustering. Okay, so that's an overview of the results in our paper. And if you're interested, I'd encourage you to take a look. I think there's also several interesting open questions about trying to really push these results as far as we can. And thank you very much.